Hello, welcome to our session, which is called Long Live Asynchronous Page Fault. A few words about us. We are both from Red Hat. My name is Vitaly, and I'm a KVM contributor. I mostly work on PV features in KVM, on Hyper-V emulation, Windows guest support, and nesting. Vivek?
Hello everyone, I am Vivek. I'm a kernel developer. I primarily work at Red Hat in storage and file system team. Right now working on Virtio-fs, have contributed to overlay.fs, kexec, kdump, block C group controllers, etc. Back to you,
Okay.
Vitaly.
Yeah, so what event are we gonna talk about today? Imagine the following situation. You have a guest running on KVM, and there is a memory access happening at the guest. And from the guest perspective, this memory is available, but on the host at the same time, it is not present, for example, because the page was swapped out. So what's going to happen in this situation? Well, under normal circumstances, KVM will have to block guest's vCPU and then handle the page fault condition. For example, bring the page back from swap. And when it's done, it can resume guest vCPU. So it doesn't see that anything happened at this time. But resolving the condition may actually take time because it involves a storage. And at the same time, your physical CPU may actually be idle because, for example, you have nothing else to run on this physical CPU if you, for example, use vCPU pinning for your guests. So what can be done? KVM uses two ideas. First idea requires the guest to collaborate. And we let the guest know that the page it just tried to access is missing on the host, but we are not blocking it. So it can actually switch to some other process and do some other work while the page is brought back from swap. The other idea doesn't require the guest to collaborate. And the idea is called synthetic APF halt. And it's the same as emulating a HLT instruction which guest actually didn't execute, but we pretend that the guest executed it. The difference between this and blocking a vCPU is that when we do the synthetic APF halt, we keep interrupts enabled. So we hope that there's going to be a rescheduling interrupt in the guest, and the guest will automatically switch to some other process. And at the same time, the memory which wasn't available before may actually become available. So when it switches back to the task, it may run normally. Today we are mostly going to talk about the first idea, which is called asynchronous page fault. Initially, it was implemented in 2010. The main concept is that there are two events. The first event is called page not present, and the other is called page ready. To deliver these events to the guest, page fault exception is being used. With every page which was not available, there is a token associated, and this token gets passed through CR2 register. Also, there is a shared memory structure, so-called like asynchronous page fault reason, which indicates that the page fault which is being injected is an asynchronous page fault and not a normal page fault. And it also tells us which event has been delivered to us. Is it a page not present event or a page ready? So how does it all work? Imagine there is a user page task and it's trying to access some memory which is not available on the host. So KVM injects this asynchronous page fault page not present event, which has been injected as a page fault exception. We get into this page fault handler in the guest kernel, and the guest kernel analyzes this shared memory structure. It sees that the event is actually an asynchronous page fault event and not a normal page fault. It freezes the task which tried the access along with the token. and switches to some other task, which hopefully won't call any faults. So what happens when this page becomes available? KVM again injects a page fault event to the guest, and we get in the same page fault handler in the guest kernel. It reads this shared memory, and now it sees that the event which has been delivered is a page ready event. It searches for the token in its internal structures, gets the task which got previously blocked, it unblocks it, so this task can now continue. So a couple of extensions were developed to this. First is called send always mode, and the idea behind it is that we can not only deliver asynchronous page fault events to user space memory access, but also to kernel memory access when the kernel itself is preemptible and can handle this. Another extension is needed when you want to run nested guests. In case this asynchronous page fault event is happening for an access while your CPU is actually in guest mode, your guest CPU is in guest mode. We cannot just inject a page fault event because it will get into your nested guest, which may not be prepared to handle this event. So we inject it as a PF VM exit. And level 1 hypervisor, your guest should be prepared to handle it. So it does exactly the same as it would do for a PF exception. So it all kind of worked for 10 years, since 2010, before people actually started looking at it closer. And the main assumption, which was well documented when this was implemented, is that the guest should actually read the shared memory structure answer to register before any other page fault, even any other like real page fault, can happen. And this should be guaranteed, but can it actually be guaranteed? There was a faulty scenario presented by Andy Lutomersky last year, and the scenario is the following. Imagine we're injecting an asynchronous page fault event, and before we manage to read the CR2 and the APF reason from the shared memory structure, an NMI happens. It is known that in Linux kernel, NMI handlers can cause accesses to user space memory, as these in its turn can cause real page fault events. So what's going to happen when this happens? Well, the CR2 register will definitely get clobbered because real page fault will overwrite it. And when we get back to the asynchronous page fault handler, we won't be able to handle this asynchronous page fault event. So what's going to happen? Well, nothing good. So we started working on it, and it's currently work in progress, but some things were already been done in the last year. So first, it was decided that send always mode for asynchronous page fault is not really robust enough, and also no existing well-known Linux distribution builds fully preemptible kernel. So the send always mode was deprecated. Second, we decided that the main problem is that the same page fault exception which is being used for normal page fault is being used for asynchronous page fault. So we decided that it's not really a good idea. And as a first step, we switched from using this page fault exception to using normal interrupts to deliver page ready events. because these events are by design asynchronous. And KVM fully switched to this mode in Linux 5.8, and KVM guest fully switched to this mode in Linux 5.9. So now the old way to deliver page-ready events is not supported anymore, neither by KVM nor by Linux guest. We also have plans to do something about page not present events, switch them, for example, to virtualization exception or check exception, but there are kind of disadvantages. Both of them have some disadvantages, like virtualization exception is only available on Intel. There were also ideas to use an interrupt to deliver page not ready exception, but in this case, we must be sure that it gets the high priority and nothing else will get handled before it. So about this interrupt, using interrupt for delivering asynchronous page fault page ready events. How does it work now? So again, the task was previously frozen because it tried to access some memory which is not available on the host, and this memory becomes available. So instead of injecting page fault exception, KVM now injects an interrupt, a normal epic interrupt to the guest. We get into an interrupt handler in guest kernel eventually, and guest kernel does the same. It searches through internal structures, searching for the task which was previously frozen with this token. It finds it and unblocks it, so this task can now run. And also, we've introduced an acknowledgement mechanism by which guest kernel tells KVM that it completed processing this asynchronous page fault event. So the next one can get delivered, either like immediately or in the meantime. So that was it. And now Vivek is gonna talk more about new usages for asynchronous page fault.
Okay, so KVM page fault error handling. So like one question is like, yeah, of course, we all talked about page faults happen. We can deliver them in synchronous manner or asynchronous manner. Now the question is, what happens we cannot resolve the page fault? What's the behavior currently and how that behavior can be improved? Before we dive into it, like I just want to address when exactly can that happen, or at least where I ran into the issues. Personally, I ran into the issues when I was running Virtio-fs with DAX enabled. And that's where I started running a bunch of the issues. Before I go further, like I just want to quickly mention what Virtio-fs is. It's fairly new, and in case you have not seen it yet, it's a pass-through file system, something along the lines of Virtio 9p, just that it's fuse-based. It allows to take one directory on the host and just export into the guest. In this diagram, the shared directory is, let's say, /4, which is being shared. Virtio-fs-d here is the daemon running on the host, which is the file server, and uses the vhost user protocol to communicate with the guest. And recently, we added DAX support to Virtio-fs. This is still in the use next tree, and we are hoping that it will be merged in this merge cycle, which is opening probably soon. What does this do is, like, typically if you're accessing a file, let's say foo.txt, you create another copy of the contents of the foo.txt whenever somebody is reading the file. We take it from the host, create a copy in the guest space cache, and that's how the guest process access the contents. But with the DAX, we wanted guest process to be able to directly map host space cache and bypass the guest space cache completely. And this probably has two advantages: that it reduces our memory footprint. On top of that, it probably is a faster access. And it just allows a better sharing also down the line, at least, because there is a single copy between multiple clients. So in this case, guest sends a request to map certain portion of the file to what IFSD, and then QEMU maps that offset and that page in the file into the QEMU address space, which shows as the physical memory inside the guest, and using DAX we can directly map into the address space of the guest process. Now, what happens if a guest process mapped a file, let's say foo.txt, and then somebody else, let's say on the host, truncates that file, and after that guest goes and does any load or a store operation to put that particular page. So the current behavior depends. So this is an error, like guest tried to access a page which is not present anymore. The file got truncated and it cannot be faulted back in. Now the question is, what do we do? If the fault is synchronous page fault, let's say asynchronous page faults are not enabled. In that case, currently we exit back to user space with an error, say eFault. But if the synchronous page faults are enabled, we kind of loop infinitely. And this is what happens. When guest accesses that page, we take a VM exit, and let's say we do a get user page as a remote, and it returns an error code, let's say eFault. But currently KVM doesn't pass that error code. And upon the return, it injects a page ready event into the guest. Guest thinks, looks like page is ready. Let me retry the instruction. It retries, again we take an VM exit, and the same loop continues. We again inject the page ready event, and this loop just continues infinitely. So basically, if asynchronous page faults are enabled, if the host cannot resolve the page fault because file got truncated, we just get into an infinite loop. So that's a problem I'm facing, and I think this problem we can have any of the resources which can be file backed, and guests can do direct load and store that memory location. I think, like for example, NVDIM, a file backed NVDIM device, will face the similar issue. So we need to do something about it. So I think there are at least two problems to fix. The one problem is we need to make the behavior uniform between synchronous faults and asynchronous page faults. I posted a patch for that, so that even for asynchronous page faults, we exit to user space with eFault if the page fault cannot be resolved. This patch has not been merged yet. There are still some concerns on the patch. I need to yet to address the concerns raised by other developers. The other bigger problem is, can we do better? Instead of exiting to user space when KVM cannot resolve the fault, can we let guest handle it? We just need to inject error back into the guest saying this cannot be resolved, and then guest can take it further. For example, if it was guest process which tries to access this page, we can send a SIG bus to the process instead of killing the whole guest. And if it was the guest kernel which was trying to access that page, we can do some exception table fix up magic to come out of that loop and return to user space with appropriate error. So that's the idea. That would be nice if we can achieve that. But how to do that? That path is not clear. Like in a few months back, we had discussion upstream, and various people have different ideas. So one of the proposals is that, at least I did this proof of concept patch. When the error happens, and we inject the page ready event into the guest, we also send error back to the guest. So guest knows whether page is really ready or not, or it's an error. And if it is an error, then guest can do the error handling. But this did not work for multiple reasons. One thing is, as Vitaly mentioned, that now we have blocked asynchronous page fault if the guest is running at privilege level 0. So if kernel accesses it, guest kernel accesses that memory location, we will not even initiate the asynchronous page fault protocol. And that means that this method is not going to work for that particular use case. And the other problem is that, at least what pointed on the mailing list, that this particular patch that is too tightly coupled with the synchronous page fault mechanism. And the problem exists even outside APF. So like design something more generic, which works both for synchronous page faults as well as asynchronous page faults. So, so this patch set was never merged, and it's just a proof of concept thing. Another idea was, I think Andy Lutomirski said, like maybe it is a good idea to use machine check exceptions. They do something similar already in the case of poison memory or something. So why not use that path and inject an MC? I think there are a couple of issues, or at least concerns there as well. Typically, typically MCs are raised synchronously only in the case of load, but stores often are silent failures. And I think later, when hardware detects synchronously that something has gone wrong with the memory, we raise an MC. So typically, store path is a synchronous path, but load path is synchronous path, and we want this to be synchronous both in the case of load as well as store. Uh, so, so maybe to solve this, maybe because we are controlling everything, maybe hypervisor can inject MC both in load and store like synchronously, and even if the real hardware doesn't do it. But I think rest of the MC code, like various copy to user and copy from user and all the code following helpers have been written with this assumption that that one can get an exception on the load, but on the not necessarily on the store. So I think that particular code path and all the helpers will require a change as well. And other concern was that MC is already pretty complicated, and there was a resistance from few people that we don't want to be doing any special casing for this case in the MC handler. Nobody has posted a patch, so this still remains an option. Hopefully, if somebody posts a good patch, hopefully it will be more acceptable. The next one, as Vitaly, I think, referred to it briefly, is virtualization exception. So there was another proposal. The Intel platform has this exception. Hey, can we make use of this to report the errors back? And not just the errors. Once we have a good race-free way to report it, we can even send the page not present events as well using this. But the concern here is it is only available on Intel. What about the other architectures, AMD and ARM64? How do we emulate there, or like how do we find equivalent replacement there? So this is an idea at this point of time. Nobody has posted the patches yet. And the last one, there was another idea. Can we handle the problem at virtio-fs level itself? Like, don't even get into this situation. Let's say implement some sort of file leases, and when one client decides to truncate the file, take write lease on the file, and that should ensure that all other clients, if anybody has the file mapped, they all unmap it before truncation happens, then go ahead with the truncation, and that should make sure that we don't run into this error situation. Maybe it will work. First of all, we don't have the concept of file lease in Fuse, so somebody will have to introduce it and devilize in the details, and hopefully we can make use of it. But still, there are some issues. So one of the most prominent one, even if we do it, it will continue to be racy because, for example, if somebody truncates a file directly on the host, it doesn't go through another virtio-fs client. That means the truncation is not going through virtio-fsd, and that means this particular user will not take any leases and not participate in the protocol, and that will be racy. I think all best we can do is the virtio-fs daemon is watching for the events and gets a notification and sends the notification back to the guest saying truncation just happened and unmap anything in this file you have. But that is still racy because in the meantime, another user can just access the file while you are being notified. So that's one concern. And not only that, I think it probably can be a stopgap solution, but virtio-fs is only one use case which can run into this issue. There are other use cases, like NVDIM was another example. If I truncate the file which is backing the NVDIM, will run into the same thing. So to me, it would be nice if this is properly solved in the KVM instead, and that will address a wide variety of use cases. So which proposal probably is most likely? I don't know. Like my hunch says, probably at this point of time, more inclined toward using the machine check exception. And if it works reasonably well, probably that might work. I don't know at this point of time, but that seems to be my preference. So that's it from me, everybody. Thank you for listening. And if you have any questions, like I'm glad to take those questions. Thank you.